In the vast expanse of the cosmos, there exist celestial wonders that have both mystified and inspired humanity for generations. Nebulae, these ethereal clouds of interstellar gas and dust, have beckoned our gaze to the heavens, sparking curiosity and imagination. In this journey through the cosmos, we will embark on a quest to understand the enigmatic beauty of these cosmic clouds, their place in the history of astronomy, their formation, and the essential role they play in the grand tapestry of the universe. Whether you're a seasoned astrophile or just someone gazing at the stars for the first time, we invite you to join us in unraveling the captivating secrets of nebulae. What is a nebula? Nebulae, the celestial enigmas that grace the night sky, come in a multitude of shapes, sizes, and colors. But what exactly are they, and what mysteries do they hold? At its core, a nebula is a vast cloud of gas and dust that can stretch across hundreds of light years. These cosmic clouds are the birthplaces of stars, planets, and the building blocks of life itself. Nebulae primarily consist of hydrogen and helium, the two most abundant elements in the universe. They also contain cosmic dust, tiny particles that scatter and absorb light, creating the mesmerizing visual effects we so often associate with nebulae. These celestial clouds come in various forms, each with unique characteristics. Whether they are illuminated by the light of nearby stars, obscure starlight with their dark presence, or are shrouded in mystery as they drift through the cosmos, nebulae are as diverse as the stars themselves. Nebulae are not mere cosmic eye candy. They are the cradles of creation. Deep within their swirling depths, stars are born. The gravitational forces within nebulae bring particles together, and under extreme pressure and heat, new stars ignite. These newborn stars not only light up their cosmic nurseries, but also give birth to planets, moons, and all the celestial objects we find throughout the universe. In essence, nebulae are the engines of stellar and planetary evolution. As we journey deeper into the universe, we'll unveil the secrets of how these stunning clouds of gas and dust have shaped the cosmos and continue to influence its destiny. A glimpse of nebulae's history. Long before the advent of powerful telescopes and space exploration, the night sky was a canvas of intrigue and wonder. Nebulae, with their ghostly presence, have left an indelible mark on the history of astronomy. The earliest sky watchers, like Ptolemy in ancient Greece, observed and documented nebulous patches in the night sky. These early astronomers used their naked eyes and primitive instruments to note the existence of these enigmatic celestial clouds. As centuries passed, astronomers like Galileo and Johannes Kepler began to peer through telescopes, revealing new details about these cloudy apparitions. Little did they know, they were on the cusp of major discoveries. The turning point in our understanding of nebulae came with the Great Debate of 1920. Harlow Shapley and Heber Curtis took center stage to discuss the nature of nebulae. Was our Milky Way the entirety of the universe, or were these spiral and elliptical nebulae other galaxies entirely? Curtis argued that the spiral nebulae were, in fact, distant galaxies, while Shapley believed they were part of the Milky Way. This pivotal debate paved the way for the discovery of the vast universe beyond our own galaxy. It was Edwin Hubble who, in the 1920s, provided the conclusive evidence that shattered the notion of a static, unchanging universe. Using the powerful Hooker telescope at the Mount Wilson Observatory, Hubble made observations that forever altered our understanding of the cosmos. Hubble's groundbreaking work demonstrated that spiral nebulae were indeed distant galaxies, each with billions of stars. His revelation expanded the known universe, demonstrating that it was not only vast, but also ever-expanding. Over the decades, the advancement of telescope technology allowed us to peer deeper into the cosmos, unveiling the intricate details and hidden treasures within nebulae. Telescopes, like the Hubble Space Telescope, have brought us awe-inspiring images of these distant clouds. The history of nebulae and our evolving understanding of them reflect the remarkable progress of human exploration and discovery. From the curious gazes of ancient astronomers to the transformative findings of Hubble and beyond, the story of nebulae's history is a testament to the ever-curious and ever-advancing nature of human exploration and understanding. How are nebulae formed? Nebulae, these cosmic clouds of gas and dust, are more than just beautiful apparitions in the night sky. They're the result of a complex and captivating process, the very building blocks of stars, planets, and the universe itself. It all begins in the heart of vast molecular clouds. These immense reservoirs of gas and dust serve as the nurseries of the universe. Inside these molecular clouds, gravity plays a pivotal role. Gravity pulls these particles closer and closer, increasing pressure and temperature as they collide. Over millions of years, this relentless process causes regions within the cloud to become denser and hotter. Within these hot, dense regions, the magic of star formation begins. Gravity compresses the gas and dust until it reaches a critical point, where nuclear fusion ignites in the core. A new star is born. As the star's energy radiates outward, it illuminates the remaining gas and dust in its vicinity, giving birth to what we know as an emission nebula. Not all regions within molecular clouds become star-forming regions. Some areas remain cold and dense, creating the ominous dark nebulae. These cosmic silhouettes obscure the light from background stars. Yet, even within these dark realms, the seeds of future stars lie in wait. Over eons, they may be triggered into star formation by external factors, such as nearby supernovae or shockwaves. Unlike dark nebulae, reflection nebulae owe their ethereal beauty to the scattering of starlight. Tiny dust particles in these nebulae scatter and reflect the light from nearby stars. This scattering process is responsible for the brilliant blues we often associate with these nebulae. The size of the dust particles determines the color, with smaller particles scattering shorter wavelengths of light. The story of nebulae is a saga that unfolds over millions of years. As stars form, live out their life cycles, and eventually explode as supernovae, they release new elements back into the cosmic cloud, enriching it for the birth of future generations of stars and planets. This ongoing cycle of birth, life, and death within nebulae is fundamental to the universe's ability to perpetually create new celestial bodies. Types of nebulae. Nebulae come in a wide variety of forms, each with its unique characteristics and origins. Here we explore several types of nebulae in detail, shedding light on their defining features and roles in the cosmos. Dark nebula. Dark nebulae are dense and opaque clouds of gas and dust that obscure the light from background stars and other celestial objects. They are often called starless nebulae because they appear as dark patches against the brighter starry backdrop. Dark nebulae typically form within molecular clouds, where regions of high-density material create areas with enough mass and opacity to block light. Gravitational forces play a role in their creation, as they can condense the surrounding matter into these dark regions. Dark nebulae are crucial to the formation of stars. They can serve as the initial stages of star formation, as external factors like shockwaves from nearby supernovae or the gravitational influence of other stars, and can trigger the collapse of these clouds, leading to the birth of new stars. prominent examples of dark nebulae include the Coal-Sack Nebula in the southern hemisphere and the Horsehead Nebula in the Orion Molecular Cloud Complex. Emission nebula. Emission nebulae are bright, colorful clouds of gas and dust that emit their light due to the excitation of their constituent atoms and molecules. This emission is often seen in shades of red, pink, or blue. Here are types of emission nebulae. Planetary nebula. These are shells of gas and dust ejected by dying low to intermediate mass stars in the late stages of their evolution. The central star's intense radiation ionizes the surrounding material, causing it to emit light. Examples include the Ring Nebula and the Cat's Eye Nebula. Supernova remnants. These nebulae are the remnants of massive star explosions or supernovae. The shock waves generated by the supernova interact with the surrounding interstellar medium, creating beautiful and dynamic structures. The Crab Nebula is a famous example. Nova remnants. Novae are sudden outbursts on the surfaces of white dwarf stars in binary systems. The ejected material forms a shell, often observable as a faint, expandable nebula. One such example is the Dumbbell Nebula. H2 region. H2 regions are areas of ionized hydrogen gas, usually caused by the radiation of hot young stars. They are regions of active star formation and can contain other types of nebulae. The Orion Nebula is a well-known H2 region. Reflection nebula. Reflection nebulae are nebulae that scatter and reflect the light of nearby stars. The characteristic blue color of reflection nebulae is due to shorter wavelengths of light being scattered more effectively. Here are types of reflection nebula. Variable nebula. Variable nebulae can change in brightness due to the varying illumination of the central star. These nebulae often exhibit fluctuations in their appearance. Protoplanetary nebula. Protoplanetary nebulae are transitional stages in the lives of stars between the red giant phase and the formation of a planetary nebula. They are characterized by a surrounding envelope of gas and dust. Emission and reflection nebulae are significant in astronomy for their role in marking regions of active star formation. They provide insights into the birth and life cycles of stars and the conditions of the interstellar medium. Other types of nebulae. Giant molecular cloud. Giant molecular clouds are vast regions in space that contain high concentrations of molecular hydrogen, or H2, making them prime sites for the formation of new stars and planetary systems. Giant molecular clouds are considered the birthplaces of stars, and they serve as the sites for the creation of entire star clusters and stellar nurseries. Bach globule. Bach globules are small, isolated dark nebulae within molecular clouds. They are dense regions of gas and dust with the potential to form new stars. Bach globules are regions of interest for astronomers studying star formation. They represent a stage where star formation is about to occur, making them valuable in understanding the process. Evaporating gaseous globule. Evaporating gaseous globules, or EGGs, are small, compact regions of gas and dust with embedded young stars. The intense radiation from the young stars causes the surrounding material to evaporate. EGGs are important in the study of young, forming stars and their interaction with their immediate environment. Solar nebula. The solar nebula is the primordial gas and dust cloud from which our solar system, including the sun and planets, formed approximately 4.6 billion years ago. The solar nebula's evolution and collapse led to the creation of the sun and the protoplanetary disk, which eventually gave rise to the planets, asteroids, and comets in our solar system. Wolf-Rayet Nebula. Wolf-Rayet nebulae are formed by the powerful stellar winds and intense radiation from Wolf-Rayet stars, which are massive, hot, and evolved stars. These nebulae reveal the extreme conditions and violent processes occurring in the vicinity of Wolf-Rayet stars, providing valuable insights into their evolution. Integrated Flux Nebula. The Integrated Flux Nebula is a faint, extended emission of scattered light seen in the vicinity of the Milky Way. It is caused by the scattering of starlight by dust in the interstellar medium. Integrated flux nebulae offer a unique perspective on the structure of the Milky Way and the distribution of dust in our galaxy. Pulsar Wind Nebula. Pulsar wind nebulae are formed by the interaction of a pulsar's high-speed wind with the surrounding interstellar material. These objects are often seen in X-rays and can be very dynamic. The study of pulsar wind nebulae provides insights into the behavior of pulsars and their impact on the surrounding environment. Supershell. Supershells are large, expanding structures of gas and dust in the interstellar medium, often created by the combined effects of multiple supernova explosions and stellar winds. Supershells play a role in shaping the structure of galaxies and recycling matter within them. They are part of the complex dynamics of the interstellar medium. These various types of nebulae paint a rich tapestry of the cosmos, revealing the dynamic interplay of matter, energy, and time. From the birth of stars within dark and molecular clouds to the awe-inspiring beauty of emission and reflection nebulae, these celestial wonders continue to captivate our imagination and enrich our understanding of the universe. Types of interstellar clouds. Interstellar clouds are essential components of the Milky Way and other galaxies. They consist of gas and dust and play a crucial role in various astronomical phenomena, including star formation and the dynamics of galaxies. Here we delve into 4 types of interstellar clouds. Molecular cloud. Molecular clouds are the densest and coldest interstellar clouds, primarily composed of molecular hydrogen, or H2, as well as other molecules, such as carbon monoxide, or CO, and water, or H2O. They are the primary sites for the formation of stars and planetary systems. Molecular clouds are typically extremely cold, with temperatures often as low as -250 degrees Celsius or -418 degrees Fahrenheit. And they are also incredibly dense, with particle densities that can exceed 100,000 molecules per cubic centimeter. Molecular clouds form through the cooling and condensation of gas and dust within the interstellar medium. Gravitational forces, external shocks, or interactions with other clouds can initiate their formation. Molecular clouds are where new stars and planetary systems are born. The gravitational collapse of these clouds leads to the formation of protostars, and the leftover material forms planetary disks. Infrared cirrus. Infrared cirrus clouds are clouds of dust and gas that emit infrared radiation. They're often found in the disk of the Milky Way and are detectable by their warm dust temperatures, which make them visible in the infrared part of the electromagnetic spectrum. Infrared cirrus clouds are diffuse and consist of a mixture of dust grains and gas. They are generally less dense than molecular clouds. Infrared cirrus clouds can form from the dust and gas expelled by stars, supernovae, and other astronomical events. They are often found at various distances from the Milky Way's plane. Infrared cirrus clouds are important in astrophysical studies, as they can obscure background objects and their radiation, including distant galaxies. They also serve as indicators of the distribution of interstellar matter in our galaxy. High-velocity cloud. High-velocity clouds, or HVCs, are clouds of neutral hydrogen gas that move at very high speeds compared to the typical rotation of the Milky Way. They are often found in the halo of our galaxy and can extend into the galactic disk. HVCs are primarily composed of neutral hydrogen, or H1, and they can have a wide range of velocities, with some moving at hundreds of kilometers per second. The exact origin of HVCs is still a subject of study, but they are thought to be associated with the interaction between the Milky Way and other nearby galaxies, or with galactic fountains, where material is ejected from the galactic disk. HVCs are important in understanding the dynamics of the Milky Way and the interactions between our galaxy and its neighbors. They also contribute to the overall gas content of the galaxy. H1 region. H1 regions, also known as neutral hydrogen regions, are clouds of cold hydrogen gas. They are called neutral because the hydrogen atoms are not ionized. They exist in their ground state. H1 regions are diffuse and typically colder than molecular clouds. They are composed of atomic hydrogen H rather than molecular hydrogen H2. H1 regions are often associated with the interstellar medium and are found in various parts of galaxies, including the Milky Way. They can form through the cooling and condensation of gas in the interstellar medium. H1 regions play a role in the study of the atomic gas content of galaxies and provide insights into the distribution and dynamics of hydrogen within galactic systems. These diverse interstellar clouds, from the birthplaces of stars and molecular clouds to the dynamic high-velocity clouds in the Milky Way's halo, are integral to our understanding of the cosmos. They influence the processes of star formation, galactic dynamics, and the distribution of matter in the universe. Lyman-alpha blob. A Lyman-alpha blob, often abbreviated as LAB, is a colossal, luminous, and enigmatic astronomical structure characterized by a strong emission of Lyman-alpha radiation, a specific ultraviolet spectral line. These structures can be hundreds of thousands of light-years in size and are among the most massive objects known in the universe. Lyman-alpha blobs appear as glowing, amorphous regions in deep sky surveys, with no clearly defined boundaries. They emit light predominantly in the Lyman-alpha wavelength, giving them a distinctive appearance. The exact physical mechanisms responsible for their formation and the sources of their intense emissions are still ongoing areas of research. The formation of Lyman-alpha blobs remains a subject of study and debate among astronomers. Several hypotheses suggest that they may be associated with the early universe, possibly linked to the activity of massive galaxies, intense star formation, or even the influence of supermassive black holes. Lyman-alpha blobs are of significant interest to astronomers because they provide insights into the early universe. Their immense size and intense radiation suggests a dynamic and energetic cosmos during the epoch of their formation. They can also help researchers understand the processes and sources that drove the re-ionization of the universe. Importance of nebulae in the universe. Cosmic nurseries. Nebulae are the cosmic nurseries of the universe, where stars and planetary systems are born. Their gravitational forces and dense regions create the conditions necessary for the formation of new celestial objects. Recycling matter. Nebulae play a vital role in recycling matter in the cosmos. As stars evolve and eventually explode, they release heavy elements back into the interstellar medium. These elements become part of new generations of stars, planets, and other celestial bodies. key to understanding star formation. By studying different types of nebulae, astronomers gain valuable insights into the processes of star formation. This understanding is crucial for comprehending the life cycles of stars and the evolution of galaxies. Astronomical laboratories. Nebulae serve as astronomical laboratories where researchers can study the physical conditions, chemistry, and dynamics of interstellar matter. They provide insights into the composition of the universe. Galactic dynamics. Interstellar clouds, including molecular clouds and H1 regions, are essential components of galaxies. Their interactions and movements influence the dynamics of galaxies, affecting the overall structure and evolution of these cosmic systems. Markers of cosmic history. Nebulae, both near and far, serve as markers of cosmic history. They reflect the conditions and events that have occurred throughout the universe's long journey, providing a window into the past. As we journey through the mysteries of nebulae, we've glimpsed the cosmic wonders that shape our universe. From the dense and light-obscuring dark nebulae to the ethereal beauty of reflection and emission nebulae, these celestial clouds have captivated our imagination. Interstellar clouds, including the mighty molecular clouds and the dynamic high-velocity clouds, play vital roles in the life and evolution of galaxies. And in the depths of space, we've encountered the enigmatic Lyman-alpha blobs, offering a glimpse into the universe's early history. But beyond their scientific significance, nebulae remind us that the cosmos is a place of wonder and beauty. They inspire stargazers, scientists, and dreamers alike, transcending borders and backgrounds. Our journey into the cosmos continues, inviting us to keep exploring, keep learning, and keep gazing at the stars. After all, the universe is vast, and its mysteries are infinite. Thank you for watching, and please subscribe to the channel.